I'm going to go ahead and share um, my screen. So, Caden, what you sent me, I don't know if you got my message, but it was like a whole bunch of just pictures with no titles or anything.
Yeah, I know. The way that he did it, he put it inside of Pearson and made it go into an entirely separate tab instead of staying
Gotcha.
on my browser. And so when I
Okay.
went to go take screenshots of it, they just didn't
Oh,
have a label.
right.
And so I tried to label them in the email, but they're just in order from 1 to 18 going through the modules of the course.
Okay. I got like, let me go back here. I got like 30 slides or something.
It's also because the way that he did it, you had to slide down to see the different parts of questions. And so I had
Yeah.
to stack them.
I don't want to scare you either, but there's some weird questions out here.
I figured.
That happens sometimes when when you take it, you go away from a big university, take it at a community college, and sometimes you get these fantastic teachers, and sometimes you get these guys that are just like showing off, you know? But
Mhm.
that's okay. We can work with that. Give me 1 second. I gotta turn this light on.
All right.
Ollie, come here. All right. All right. So Kayla uploaded some exam questions too, some former exam questions from UW. You can kind of just bounce back and forth if you guys want to. There's no rules here. We've got time, and we only got two people on here, so that's good too. Um, does you guys, one of you just want to start with one of the questions?
Yeah, I can look for one.
So I
I haven't taken those old exams yet, so um I don't know which ones I don't know how to do. But if we don't have a strict agenda, what would be really helpful, at least for me, would just be going over some of the when you get this type of problem, this is how you approach it. Just sort of the
yeah,
steps. Maybe st like for example with looking for the name of what it's called, like partial fraction decompositions, just like strategies for those problems type of thing.
you got it. Um, let's see here. So the other, do you know the what year that other exam was that you sent it to me? I got
It's
2017 and then 2000. It didn't really say what year it was.
I don't know. They're both old. The way my exam is set up is it's 10 questions and they're multiple choice. And then 90% of your grade is the work you show that supports which multiple choice you pick. And then 10% is just if you pick the right one.
Okay. All right. I got way too many screens open here right now. Let me go back. Um, just download this one too. We'll get the ball rolling here in a second. Uh, do you think so? Let me open this one real quick.
I mean, I can ask a specific question too. So the way I guess my question is about the approach. I've been trying these problems differently, where sometimes I start with like the A times whatever it's next to plus the B times whatever it's to. Sometimes I expand it, and then sometimes I sort it by like x to the fourth and what that's multiplied by, and then x to the third and what that's multiplied by. Is there one of those ways you recommend more than the other, or just sort of try for whatever problem it is, which approach works best?
What are you talking about for partial fractions?
Yeah.
Okay, yeah, for partial fractions, there's three different types of problems. Um, I'm looking on your exam for a partial fractions question. Um, let me look through the second one. I didn't see one on the
Yeah.
2017.
I have one I have one I could give you.
Okay, let's do it.
Okay. It's integral of 4x plus 5 divided by parentheses x minus 1 and then second parentheses x squared plus 1. I can say that again. So x minus 1 and then x oh, I actually wrote x plus 2 squared. Sorry. There we go.
Quantity like that.
Yeah.
Okay, can you guys both see that? It's
Yep.
just like that. Okay, so let me just fix this a little bit. So there are three types of, so what you want to do for techniques of integration, you said x plus 2 squared?
Yeah.
Okay,
Yeah.
so for techniques of integration, we have three different types. Or for all the techniques of integration, it's basically three different types. So trig integration, you're going to have a few offshoots here and there. So what you want to look at is on the school classroom, right? You go to the classroom and then scroll down, and there'll be a class on techniques of integration. And in there is got all the different techniques of integration and what the types are, right? So I call this one type 2. Now, the thing with types 1 through 3, integration by parts and trig sub, is that you only have those three types. You only do one at a time. But with partial fractions, you could have a whole bunch of different things going on, right? You can mix up the different types. So type 1 is just linear terms. Like if I didn't have this right here, I'd call that type 1. That would be a type 1 setup. This here I call type 2 because you have a repeater. Right now, if I had an irreducible polynomial, x squared plus a number, that's going to be type 3. Okay, so they all have different kinds of setups. So what you can do is you can look at this as the integral of a over x minus 1. So that's your type 1 style setup. Okay, and the next thing you would do was like b over x plus 2. So this is type 2 setup. When you have a repeater, you count up to it, right? So if it was cubed, I would have another term, right?
So do you only have to do bx plus c over the x plus 2 if it was like x squared plus 2?
That's right. So if I had integral, well, let's just say I had something like this, 1 over x plus 2 x squared plus. So x squared plus cannot be factored, but x squared minus can be factored into conjugate pairs. So when it's x squared plus like this would be a over x plus 2 plus bx plus c over the irreducible polynomial. So once you realize that there's only three types. There's only three types of setups: linears, repeaters, right? Where you've got to, the repeater, you've got to write it as many times as you see powers. So if it was to the 3, I'd have another one that would say d over x plus 2 to the 3. Does that make sense? Yeah. And then the other type is that guy right there. So you can have all of these different types in a single problem. All right. But once you know that setup, you just have to follow a procedure. All right. And since there's only 2 people here, you guys don't have to mute your mics. I know you guys do that in classrooms and stuff like that because there's like 20 people, but we only got 2 on here. So if you got questions, just blurt them out. Right. So does that make sense how we got that set up?
Yeah.
3 things you need to worry about. So that's what makes integration by parts so great, is because you only have 3 things to worry about with each one, except for the whatever it's called, the trig, right? The trig one's a little bit different. Okay, 1 second here. There we go. Okay. I've only done live on school a few times, and there's all these, like, you got to trick the system, but we've got it. No worries. So, okay, that's the setup. Okay, that's the first setup. So once you get that set up, you're going to start going into the math, right? So I'd call this maybe step 1. And then the next step, what you're going to do is you'll go actually, let's do it like you go 4x plus 5. You're basically going to get a common denominator. So you're taking this apart. You're doing reverse common denominators, what you're actually trying to achieve in the end, right? So what I'm going to do here is I want everything over x minus 1, x plus 2 quantity squared, right? So I'd multiply the a times x plus 2 quantity squared, right? And then the b is going to get multiplied by x minus 1 and x plus 2. So I just multiply by what's missing from the common denominator. So this step right here is kind of overkill. You can do this step if you want to. And I'd say at first, when you're practicing this, you should probably do this step. But see, once you get a common denominator like this, once the denominators are equal, that forces the numerators to be equal. You see that? So once you have a situation like this where your denominators are equal, that forces these numerators to become equal. Okay, so the only thing you really need to write down when you're doing this is the numerators. So you might do that for the first few repetitions of a problem. And what you want to do, since we have, so here's a whole psychology of what's going on here. You're having an experience, and this is the best way to learn is through an experience. So when we're done with this session, you're going to want to take the video that I post along with the notes that I post and go back over it because it's going to trigger that memory, right? It's going to solidify it more in your brain because, you know, you can go through this whole thing and you can say, yeah, I understand it, but will you remember it, right? So really, you just want to make your numerators equal to each other. So if you want to skip that step and just say to yourself, you know, set the numerators equal to each other and make the right-hand side just multiply by my missing terms from the common denominator. Does that make sense?
Mm-hmm.
Okay. Taylor, did I tell you I went to Wisconsin?
Yeah. I'm taking the class through University of North Dakota randomly just to transfer credit. So this class isn't because Wisconsin gives you practice exams, this course doesn't. But yeah, I go there during the year.
Okay, cool. I used to live on Mifflin Street.
Okay, cool. Yeah.
Okay, enough of that. We don't want to leave you out, Kaden. All right. So now that you have this, it's like the fundamental theorem of algebra, right? What common terms on both sides of the equation have to be equal to each other. So your coefficients of x squared on both sides have to equal each other. Your coefficients of x have to equal each other, and your constant coefficients have to equal each other, right? So you can use that trick. But before you use that trick, because you got to expand it and everything like that, what you can do is you can look at all the zeros, right? So like if I plug in x is equal to -2 here, I'm going to get a 0. If I plug in x is equal to 1 here, I'm going to get a 0. So I can take advantage of that and I can say, all right, well, if x was equal to -2, what would I have? On the left-hand side, you'd have -8 plus 5, right? If you plugged in x is equal to -2, your a term will go away, your b term will go away, and you'll get c is equal to c times -3. See how I got that? Right? And then 5 minus 8 is -3, right? So you have -3 is equal to c times -3, which forces c to equal 1. And so you just hold on to that. Okay? So you're going to do, when you have only type 1s, you can do this trick until the end. If you have a type 2 and or type 3, you at the end, you'll have to pull the common undetermined coefficient method, right? And I'll tell you what that's all about. So if I put x is equal to 1 in here, right, that's going to make some terms vanish. So I'll get 4 plus 5 on the left-hand side. On the right-hand side, I'll take a times, that would be 3 squared, right? So you're going to get 9 is equal to a times 9, which will also force a to equal 1. Okay? Now, I don't have that b term. Notice if I put x is equal to 0 in there, that will give me my constant coefficient. Okay, and I already have a and I have b, so I want to make sure that we talk about this. We don't absolutely have to use it here, but we might or probably will have to use it in later problems. So let's talk about this comparing coefficients thing. So if I expand this whole thing out, I'm going to get ax squared plus 4x plus 4, right? And then here I'll get plus b x squared, what, plus x
-2.
minus 2 plus c x minus 1. Now here's the trick. You can equate all of your x squared coefficients on the left and the right hand side. So I'm going to be a little redundant here. This is going to be overkill because we already have 2 of the values. We don't need all of them. But for the x squared, I have 0 coefficients of x squared on the left hand side. But on the right hand side, I've got a plus b. Okay. Well, that means that a is equal to negative b. So since a is equal to 1, b is equal to -1. And you can check your values here too, right? Because I can say, all right, well, I have a coefficient of x on the left-hand side, which is 4. And the right-hand side, this would be 4a plus b plus c, right? And would this be correct if we use this? So you have 4 is equal to, a is equal to 4, b is equal to -1, and then c is equal to +1, right? So that would equal, that checks out. That works. So we just checked our values in the coefficient of x. So if you want, you can expand the whole thing out and do it this way from the very beginning, but you're going to have a system of equations if you do it that way. So the way I like to do it first is plug in points, plug in x's that are going to make these guys go to 0. Do that first and then go down here and start looking at the coefficients, because I could look at the constant coefficient too, and notice the constant coefficient is always going to be when x is equal to 0. That will always give you the constant coefficient. So that's going to be 5 is equal to 4, 8 times 4 plus, well, minus 2b minus c. So you can do it this way right off the bat, but notice if you do it this way right off the bat, you're going to have a system, and systems are a pain to solve. So plug in your x's that will make certain values disappear. And then once you've exhausted all those, then you notice, like right off the bat, the first one we did gave us our missing term. See that? Because I already knew a and c. So I was able to go down here and figure out what b is by just looking at the coefficients of x squared on the left and the right-hand side. So that's an old trick that's going to come up now and again. If you're taking differential equations later, you're going to be using this as well. So just know that the coefficients of x squared on both sides have to equal each other. The coefficients of x and the constant coefficients have to equal each other as well. Is that all making sense? Right on. So now that I have all that, I can go back up here and I can plug them into my integral. See, I've got the integral of a is 1 over x minus 1. Plus b is -1, x plus 3, and then c is 1 over x plus 2, quantity squared dx. Okay. So I just found those values. Now there's a few of these that you're going to want to memorize to make your life easier. So remember that, you know, the first few, like ln, absolute value of x minus 1, that's easy. Minus ln of x plus 3, that's easy. And then this next one, remember that's x to the -2. So I'm going to add 1 to the exponent and divide by that number. So this is going to be -1 over x plus 2 plus c. So that's your answer. Okay, and what I'm going to do is write down a few of these that are going to help you. If you just memorize them, you don't have to. See, I memorized this. I'm not going to write this thing as x plus 2 to the -2 dx. Well, you know, I could add 1 to the exponent and divide by that number, right? So that's x plus 2 to -1, and then you're dividing by -1. Right, you can do this if you want to. Right, but since that one is a type 2, that's probably going to come up again, why not memorize it? Right, but this is your answer for this problem. So you can see what happens. Your first step is to set it up. And this is where a lot of people screw it up. Your first step right here is to set it up correctly. Depending, do I have just linear terms? If I just have linear terms, it's a over the linear term plus b over the linear term. If I have repeated terms, right, I got to make sure I count up to that and include them all. And then if I have any irreducible terms, I got to include those too. I'll go over those, right? And then you set it up. You really only got to set up this because you just say, I'm going to multiply by what's missing from that common denominator. See, what I'm missing up here for that A is x plus 2. So I'm just going to multiply that A times x plus 2. And then the B is missing an x minus 1 and an additional x plus 2. And then this guy right here is just missing an x minus 1. So I can skip straight to this step. Then once I get there, I'm going to plug in x's that are going to make terms go to 0. X is equal to -2 will make these two go to 0. X is equal to 1 will make those two go to 0. So that way I can just isolate these guys, right? And once I'm done plugging in, terms, I can then match coefficients. And honestly, the easiest one to match is the constant, because if you plug x equal to 0 in there, that's going to give you the constants on every side, right? You can do it like that. Or you can just simply look at the coefficients of x squared, but you probably want to expand this out. Now, some of these are easy. Coefficient of x squared, I can just look there, right? I'm not going to be able to go. I don't really have to expand this out to see that there's going to be a coefficient of x squared there. Does that make sense? Okay, so what would you do if you had something like, let's say we've got just dx over x minus 1, and then you had like x squared plus 4, and then you went ahead and squared that. So see how they're combined? I've got a type 1, which is a linear term. I've got a type 2, which means you're repeating terms. And then type 3 is irreducible. So what you do here, the way you set this up, this will be a over x minus 1 plus bx plus c. Since it's irreducible, x squared plus a number will always be irreducible. And then you got to go dx plus e to get your second one in there. And this type of problem, if they give you something like this will be a set up. They'll just have you set it up because this is pretty impossible to do, right? They might ask you to do that. They'll just set it up. Okay. Now, there are integrals you want to memorize, right? So if you have, let's say dx, this one will look familiar, a squared plus x squared, right? So if I have, two dx's. If I have 1 over 1 plus x squared, that's tangent inverse, right? So this one here is 1 over a tangent inverse of x over a plus c. Okay. So that's one to just have kind of off to the side. Let me check my notes on one thing here. Okay. So that's one that you want to memorize. I mean, obviously, if you have dx over, let's say you have a coefficient, right? It's just a linear term, but you got a coefficient. This will be 1 over a ln of ax plus b, right? Because that's use substitution. You're going to get that a from the chain rule, so it just comes out, right? And then if you have, let's say, dx over x plus a, and you square that thing. This is the one we just did. This is going to be -1 over x plus a, -1 over x plus a plus c, right? So if you know some of these basic ones, you'll be good to go. Oh, what about this one? No, I think that's about it, right? I mean, the big ones that you have to know, the big one that you have to know that would be difficult to derive is that one. I would definitely memorize that equation because it's going to come up over and over, and you don't want to do trigonometric substitution every time the sum of two squares comes up in the denominator. Okay? It doesn't work, though. This won't work if I had an x on the top, though. If I have one single x on the top, that's use substitution. If I have x squared on the top, I'm going to have to use trig substitution. Does that make sense?
Yeah.
I mean, so with this in your memory, maybe go back over this later, but definitely go into the school, right? And look at the techniques of integration where I go through type 1, type 2, type 3, and then a mixture of all of them all together. And you want to rewrite the problem and say it out loud as you rewrite it, right? You want to make a really big deal about it. So you're memorizing a procedure. And this is what people really don't do in math. They watch somebody else do it and they're like, oh, I'm going to try this. And no, don't do that. Practice it first, right? It's like playing guitar or playing sports or any kind of musical instrument or any kind of sport, really. You want to repeat that procedure over and over and over so you can hit it using muscle memory. The great thing is with mathematics, you don't have to do a million repetitions. You know, it doesn't take any kind of physical ability. It doesn't take an ear for music. You just have to practice this procedure. See, this covers 1 and 2 right here. If you rewrote this a bunch of times and paid attention to the procedure, like say you wrote it 3 times and you paid attention to the procedure and you talked yourself through it and you made a big deal about it right while you're doing it, the next time that problem comes up, you're prepared. Right? As opposed to like just watching somebody else do it and then go home and try to do it and fall on your face a bunch of times. You ruin your confidence. You say, I'm not a math person. I suck at math. You know what I mean? That's just because we're approaching it wrong. Yeah. Any other questions on partial fractions? No. I definitely want to hit each technique of integration. And then I saw, so for yours, Caden, he's doing approximations where they're using sums. We want to memorize those setups. So those are just setups and equations, right? And we could talk about those a little bit later after we hit all these techniques. And as far as the tables are concerned, I've seen that done before where you have to match up the type with it. And then like you'll have it on the table, they'll write it as a U, but you're dealing with it as an X. You've just got to translate between the X's and the U's. Does that make sense?
Yeah.
Yeah, we can look at that too. But let's make sure we hit all the techniques of integration before we run out of time or anything, you know? Okay, we can move on to whatever you want. We can do trig sub. That's a good one to get into next.
Yeah, let's do that.
Okay. Let me do one thing here. Yeah, see, I was looking for this when I saw those tables. I honestly have not seen tables where they have you use tables like that in a really long time. You always get that at the weird stuff like that at different schools. But we can work through it. It's no big deal. So let's talk about trig sub. I'm recording this too. You guys are okay with that?
Yeah.
Oh, it turns out I was not recording any of that stuff in the very beginning. I forgot to unpause it. Man, I have a nickel for every time that happened to me. All right, what you're going to do is pay attention to 3 different kinds of expressions. This is what's going to trigger you to use trig sub, right? Now, so you've got a squared minus x squared. So if I have the square root of x squared minus a squared minus x squared, so you have a constant, it doesn't have to be squared. It can be 7. Doesn't matter what this constant is, but the constant comes first, and then I'm subtracting the variable, right? And the substitution we're going to use is x is equal to a sine theta. So that's what's going to trigger us. That's what's going to trigger us. Okay, and then there's an identity you're going to use with this, which is 1 minus sine squared theta equals cosine squared theta. But I'm going to show you a little trick here. You don't need the square root. You just need an even denominator in the exponent, right? So notice this is to the 1/2. It would also work if this was 2 over 2, which is just a minus x squared. It would also work if it's 3 over 2, right? It would also work if it's 5 over 2 instead of the 1/2 that it's already in. So it doesn't have to be a square root. It just can't be a 3rd root or a 5th root or something like that, right? But here's the big trick. This is the part that's like most difficult with these problems, is simplifying this thing while it's inside the integral, right? Every time this happens, every time I get a type 1, I'll have a squared minus x squared. This guy right here will always equal the sibling, right, of sine, which is cosine of theta. That will always equal a cosine of theta. So this is type 1. It's we're going to memorize is type 1 trigonometric substitution, right? So you learn to identify that, and then you execute a script, right? That's going to be the challenging part about this section is that you're going to have integration by parts. You got to learn to identify that, each of the 3 types, execute a script, right? Trig sub, and so on and so forth, right? Now for type 2, that's when you're going to have the sum. So you have x squared plus a squared. Well, for this, your substitution you're going to use is x is equal to a tangent theta. A tangent theta, right? And then you'll use the identity 1 plus tangent. To simplify it, you're using this identity. But look, you don't have to do this. If they don't make you show your work, you're not going to use that at all because you know the trick. The trick is that this expression will always, 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 a squared plus x squared plus a squared, doesn't matter. But this expression will always come out to be equal to a secant theta, right? Tangent and secant go together just like sine and cosine go together, right? So when you have trig sub type 1, notice that your substitution to be a is equal to x is equal to a sine theta, but this expression will ultimately reduce that. So that's your cheat code right there, right? Your cheat code right here, notice this is a tangent. That's going to be your substitution. This will always end up being a secant, right? So this is worth its weight in gold right here, right? If you can memorize this table. Then you have type 3, the final type, right? Type 3. This is when the x comes first, x squared minus a squared. Well, here your x will be equal to a secant theta. The identity that you would use, which is the same as the last identity that I wrote down, it's just in a different order, is secant squared theta minus 1 is equal to tangent squared theta. Okay, and these two guys are the same, right? You want to know those anyways. You want to know that sine squared plus cosine squared equals 1. 1 minus cosine squared is equal to sine squared, and so on and so forth. Those are your Pythagorean identities. And then your cheat code for this, right, is that this guy right here, x squared minus a squared, that will equal a tangent theta, right? So for this whole thing, this whole trig sub stuff, I'm going to post this too, just so you know, I'm going to post these this PDF along with the video, which is missing partial fractions now. I'm going to post that so you'll have this too. But this, you want to write this down a bunch of times. Like honestly, if you take this guy right here and put it on the mirror in your bathroom, right? And then take this second one and put it, tape it to a piece of paper on your front door, you know, and then maybe take this one and put it on your fridge or something, right? Whatever you need to do, just so you're like, you see, when every time you see it, you're going to say it to yourself. Type 1 is when the constant comes first and I'm subtracting x squared. That's x is equal to a sine theta, and that root sign will always equal a cosine theta. If I took 60 seconds of my life and just repeated that for 60 seconds, I could probably repeat it 10 times. And 10 repetitions of saying that over and over is going to do some damage, right? I'm definitely going to have a better chance of remembering it, right? And then you do some problems, right? So let's just say I have the integral, unless you guys got a good one you want to look at. But you'll notice that it doesn't matter what problems you do as long as you go through each different situation. And what you'll notice too is that it doesn't matter what the types are. Once you get this procedure down, I can change the type, no problem, because I do all the problems the same. It doesn't depend on the type. The only thing that the type says is what to substitute. It doesn't change the procedure. For integration by parts, each different type is going to have a different procedure based on a table, right? This will not be like that. Okay, so immediately I recognize that the constant comes first. It's a squared minus x squared. So this is, I'm going to write this down. I'm going to make a big deal about it. This is trig sub type 1. The constant is coming first. And in type 1, and maybe I'll make a little note here. Type 1 says x is equal to a sine theta. And then my little cheat code is that a squared minus x squared will always equal a cosine of theta. The more times I can say that, repeat it, make a big deal about it, better off I'm going to be. Okay, so we haven't done U substitution, but if you look at the videos, there's videos on U substitution. I do steps 1, 2, 3. The first step in any substitution is declare your substitution. This would be x is equal to a, which is 3 sine of theta. So I just take the square root of whatever that constant is, right? Looking good? And the next thing you always do once you declare the substitution, the next thing you're always going to do is take the derivative. So this would be 3 cosine of theta d theta. And after everything's done, what I'll do tonight is, Caden, I'll take all those questions and I'll type up solutions. You said there's 11 questions total?
18.
18. I got like 30 some slides, so I'm not really sure how that's work. I'll take a look at it and I'll type up some solutions. You can look at it and tell me if I left anything out or whatever. And then Kayla, I'll take yours and I'll make solutions for those too. It doesn't take me long at all to type up solutions, and then I'll post them.
Okay.
So you'll have those to rewrite, and then you'll know what I'm doing, because I'm going to do it the same way. I'm going to do all this stuff in a similar fashion. Okay. But I mean, if we go through this trig sub stuff, just like we did the partial fractions, once you get to one of these problems, you're going to know what to do, right? There might be kind of a funky one in there somewhere, but if that happens and you get caught, you just send me a chat. Just send me a message on school. I'll get back to you as soon as possible. Right? Pretty quickly over the summer. I don't have much going on right now. So now that's step 1. So step 1 is declare your substitution, take the derivative. That's it. The same thing with U substitution. U substitution basically says if the derivative of the thing inside the function is sitting on the outside, that's U substitution, right? This is a little bit different. So at step 2 here, I'm going to actually, there's no bounds. That's one thing to note here, is that this is the substitution of an indefinite integral. The bounds are not defined, right? So step 1, 2, 3 is going to be pretty smooth. If the bounds are defined, I would have to take the bounds and change them in step 2 after making my substitution. So what I just did here is I went from x to theta, right? If I had bounds here, these would be x bounds. My next order of business would be to change those bounds. And I'll do an example of that, right? So here we got this guy. Now I've got to plug everything in to this guy right here. Now let me show you the hard way. The hard way would be to go square root of 9 minus 9 sine squared theta. So I just replace my x squared with 9 sine squared theta. And then I replace my dx with 3 cosine theta d theta. Okay. And I'll put that over the top of x squared, which is 9 sine squared theta. That's all great. But see that root sign, I got to simplify. That's the goal right now. Now, if I take all of this stuff that I've got with my integral and I go and simplify that root sign with all this baggage and carry that through 5 steps, I'm going to make a mistake. Okay. So if you've got to show your work, if you don't have to show your work, that root sign is 3 cosine theta. This root sign right here is 3 cosine theta. I know that. That's my cheat code right there. Look at that. 3 cosine theta. I already know what the answer is. I already know what this is going to simplify to. That's wonderful. Now, if you got to show your work, here's what you want to do. You want to take a little side note. You don't want to write this whole thing. You want to go, all right, square root of 9 minus 9 sine theta, sine squared theta, right? Now, if you look at these guys right here, this is the identity I'm about to use. I'm about to use this identity. Okay? And that's going to be, you pull out the 9, right? You got 9 1 minus sine squared theta. And I want to train my brain to when I see 1 minus sine squared theta, I know right away that's going to be 9 cosine squared theta, which is going to simplify to, guess what? 3 cosine of theta. Exactly what I thought it was going to be. So when you're taking a test, confidence is the name of the game. It's the name of the game. Confidence is the name of the game, right? So if I am having answers come up and I already know what the answer is, that's going to make me feel pretty good. If all of a sudden I'm looking at something and I can't recognize what's going on, fear sets in, the amygdala fires, and next thing you know, I'm in the sympathetic nervous state, place you don't want to be, right? That's when you start panicking, your leg starts bouncing up and down. You guys have seen that in exams before. But if I simplify this now here, I don't have to simplify it while carrying all this baggage with me. If I've got to write all this kind of stuff right here, all those times, I'm going to make a mistake. So if I'm grading, I've graded 300 of these papers at one time for a class. If I'm teaching at the university, got 300 students in that class, I've got to grade 300 of these problems. And you know where I see the mistake every time? The mistake is always in simplifying right here. So don't do it. Don't do it. Because if you write something down enough times, it's a game of telephone. You're going to eventually make a mistake. So this guy right here, I'm going to write all this stuff right here first. I'm going to get this simplified. This root sign has got to be simplified. I'm going to simplify that first. Then I'm going to write down 3 cosine theta along with my dx, which is 3 cosine theta d theta over 9 sine squared theta. All right. And then the 3 times 3 is a 9. That's going to cancel. Right. And what I'm going to end up with cosine squared over, this is cosine squared theta over sine squared theta d theta, which ends up being, so this is where it gets tricky, right? We don't want to do any thinking here because when something like this comes up, we're going to have to think a little bit. So if I have all of this stuff down up to this point, muscle memory, I've really exhausted little to no intellectual horsepower here. I'm going into this cotangent squared, a little fresh. Now there's one other Pythagorean identity. I want to show you guys this real quick. All right. Notice if I've got sine squared theta plus cosine squared theta equals 1. You got to memorize that. If I take that whole thing right there and I divide that by cosine squared, let's say. If I divide this whole top by cosine squared, I'm going to get tangent squared theta plus 1 is equal to secant squared theta. See, that's where that comes from. That's where your other Pythagorean identity comes from. If I divide the whole thing by sine squared theta, I get my third and final Pythagorean identity, which is 1 plus cotangent squared theta is equal to cosecant squared theta. Okay? So I want to write that down a few times because I want my brain to trigger when I see it, right? It's called the Baader-Meinhof phenomenon, frequency illusion. The more times I say this and write this, the better the chances my brain's going to fire when I see cotangent. Because cotangent squared, actually. Because cotangent squared is cosecant squared theta minus 1. Okay? Now, I know what you're saying to yourself. I would never see that. And that's what we tend to say to ourselves when we see new things like this. We go, I would never figure that out on my own. Don't say that. Because there's not going to be like an infinite number of things you're going to have to figure out on your own. Every once in a while, these things are going to come up. So you say, now I know what to do. Now, when I get cotangent squared, which could happen, there's a big bucket of problems I can choose from for this class. And I've seen them all, and there's not that many, right? So there's not a lot of surprises they can hit you with. So what you do is you say, okay, this one goes in my bank. I know that cotangent squared theta is equal to cosecant squared theta minus 1. So instead of saying to myself, I would never see that, I'm going to say, now, if that comes up, I'm going to see it. Right? Because it's not an infinite number of things they're waiting to get you with. It's little things like that. Does that make sense? There's something I know about cosecant. I know the integral of cosecant because I know the derivative of cotangent is negative cosecant, right? The derivative of cotangent is negative cosecant. So there's going to be negative cotangent theta minus 1 minus theta plus c. There you go. And that's that's close to your answer. We're not there yet. Okay. Because we got to go into step 3. And step 3 of any use substitution or any kind of substitution is back substitution. You got to go backwards now. Okay. Now, some schools will allow you to just say, all right, well, I know that x is equal to 3. I mean, most schools will let you do this. Some are going to want, like, it's all up to your teacher, right? Because, see, this is sine inverse of x over 3 is equal to theta. I can put that in for theta. I can do negative cotangent of sine inverse of x over 3. That's up to your teacher, though. Some of them are kind of brutal about that, right? So if you want to err on the side of caution, draw a triangle, put your theta there. Now, I know sine is opposite over hypotenuse, right? Does that make sense? And then what goes in that missing spot? In that missing spot goes the term that got you into this mess in the first place. So I could figure out what cotangent is. I know what cotangent is. Cotangent of theta is equal to 1 over tangent. So that's cosine. Well, I should already know this, cosine theta over sine theta, which is going to be adjacent, right? Over opposite. So I can figure out what cotangent is. Now, the only way to get theta, though, is with that sine inverse. So your answer in the end is going to be negative square root, be very careful, 9 minus x squared over x minus sine inverse. This is all you can write for this. You can't really do anything else. Plus c. That's your answer. So these are very involved, right? But if you'll notice something, you got that stuff memorized. You got the table memorized that we just did on the previous page. You got this table memorized. Then you go into the problem. Now all you got to memorize is steps. Step 1, declare your substitution, take the derivative. Easy. There you go. I got that. Step 2, don't write this whole thing out right away. Figure out what this root sign is going to be. You're going to want to show your work. If it's a multiple choice question, just take that square root and say that it's 3 cosine of theta because you memorized that. It's going to be a cosine of theta because our substitution was a sine of theta. What goes with sine? Cosine, right? Put that in, simplify. So this part right here was the only tricky part. I've already got half the points, maybe more, right? And if I get something like this, just remember I can either rewrite it somehow. I could rewrite this maybe somehow. But when you see cotangent squared, cosecant squared, sine squared, tangent squared, cosine squared, secant squared, it's probably going to involve one of the 3 Pythagorean identities. And this isn't unique to this problem. That's why I chose this problem, because if you can do this one, you got a lot of bases covered. Right? They might just give you, 1 over x squared plus 1, or 1 over the square root of x squared plus 1, right? Something like that. Is this making sense? I mean, we already know, let's just take a little side note here. We already know what this is. That's tangent inverse. But let's say we forget what it is. Okay, well, I know this is trig sub type 2. The only thing is, I usually have the square root of x squared plus a squared. Okay, that's fine. Just because I usually have a square root doesn't matter, right? x is equal to a tangent theta. This guy right here will be a secant theta, right? So without that square root, I'm going to have a squared secant squared theta. So if you don't have a square root, don't worry about it. If you have a 3/2, don't worry about it. Just go through the process and be careful. Because I can say step 1, x is equal to tangent theta, because my a is equal to 0. I take my derivative, dx is equal to, what is it, secant squared theta? Make sure you got those. If you don't have your, there's two things I want to do with you guys before you get off, right? I want to make sure we go through the trig table and 5 laws of exponents, which sounds really silly, but you'll have to trust me on that one, right? Especially when you get into series. Okay. So I have that. Now, part 2, right? I know I can go through the whole process, right? I can say 1 plus tangent squared theta, and I know that's equal to the square root of secant squared theta, which I know is equal to secant theta. But I don't need the square root. See, on the bottom, I just have 1 plus tangent squared. I don't need to think about this in terms of a square root anymore. See, that's what I'm going to have on the bottom. Does that make sense? So what do I got here? Step 2, I've got to write the integral. So I'm going to write the integral. And on the top, I got my dx, secant squared theta, d theta. On the bottom, I have secant squared theta. I don't have a square root sign. Okay.
Wait, sorry, can we go over that one more time? Why can we just get rid of the square root?
I didn't need it. I didn't really need it in the first place. Right. So I see that, like, this is, if you think about this, this is 2/2. Yeah. And don't be afraid to ask questions, because if you got a question, I guarantee the other person is probably thinking the same thing. Right. This is 2/2, isn't it? Because it's to the 1. When I have a square root, that's equal to x to the 1/2. So I can use this substitution as long as that denominator of my exponent is 2. Right? So I can still use the trig sub here with this whole idea, x is equal to tangent, go through the whole process, and then I don't really, if I know this procedure right here, that I'm going to have to do this, I don't really need to do it with the square root. I can just say, well, my x is equal to tangent. What do I have right here? This guy right here is 1 plus tangent squared. How can I write that? Right? I don't need to get it out of the square root, but it's a lot better like that, isn't it? And then what I see is that these will go away. And that tends to like, for what is it? The square root of x squared minus 1 is sine inverse or something. I don't have those memorized. I really should. I've been doing this for like 30 years. I still don't have them memorized, but you can find them really easy, right? So whenever you have the sum or difference of squares, as long as your exponent is not 1/3, 2/3, something weird like that, you can use trig sub. You don't have to have a square root. So if you ever see the sum or difference of squares in a problem, especially in the denominator, you know you can hit it with this. You don't need a square root, right? And we think, like, we look at this and go, I'm going to remember that, right? Chances are you won't. And 24 hours from now, this is dust, right? So what you want to do tonight before you go to bed, here's the trick. There's something called the power hour, right? So right before you go to bed at night, whatever you do within a half an hour to an hour before you go to bed, your subconscious will marinate in that as you sleep. True story. If you watch a scary movie before bed, you tend to have nightmares, right? Because when you're in that REM cycle, see, all my friends are neuroscientists. This is where I get all this shit from, right? So when you're in that REM cycle, you're converting that short-term memory into long-term memory, and it's usually what happens right before you go to bed. We are doing subconscious training right now. The more I say this to myself, the better my odds when I'm relaxed on an exam, it's all going to come through me. Because that's what intuition, that's what instinct is. It's subconscious training. It's a result of proper subconscious training. So if I do that before I go to bed at night, and then I wake up right in the morning, when you wake up right in the morning, half your brain is asleep for almost an hour. And that is when you're highly influenced, right? So if you hear a song first thing in the morning, you cannot get this song out of your head. Does that ever happen to you? You wake up and you hear a song right away and you're like, oh my God, I can't get that out of my head. Or you wake up and you get some bad news and you're in a pissed off mood for the rest of the day. right? Or if you wake up in the morning and you're like, today's going to be a great day, and you list all the things you're grateful for, you're going to tend to have a better day, right? So that hour after you wake up, you're highly suggestive. You're in a state of hypnosis. So if I do the exact same thing the night before, the next morning, that's going to stick with me, right? So if you have trouble with a problem like this, or trouble memorizing this or keeping it, I would write this 3 times tonight before I go to bed, and I wake up tomorrow morning and write it 3 more times. But as I write it, I'm not going to just write it. I'm not just going to look at it. I'm going to engage with it. I'm going to write it, maybe even on a whiteboard if you got a big whiteboard, or on a piece of paper. It doesn't matter. Maybe with a big crayon. I don't know. Make it distinct, but say it out loud as you write it, and that's going to help influence that subconscious memory. Carl Jung wrote a lot about it, right? And he knew the subconscious mind. So those are some tricks, right? Any questions about that stuff so far? Because I'm going to hit you with the good one next if you want to keep doing trig sub. So we're going to have to move on to integration by parts and trigonometric integration here soon too. I don't know how much time you guys got, but I got plenty. Let's change it so you got bounds. What if you have 3 square roots of 3 over 2, 0, x cubed dx, 4x squared plus 9. Just like that. See, now I've got some wacky looking thing on the bottom. I've got bounds too. So between the last problem we just did and this problem right here, we're going to cover just about everything. Every contingency you want to be prepared for. Bounds and something where it's not the square root. This is the cube of the square root. And I want to be, so here's, when something is familiar, it doesn't fire the amygdala, right? So millions of years of evolution, you see something in your environment that doesn't make any sense, your amygdala fires, fight, flight, or freeze, right? We want to stay out of that sympathetic nervous state. You want to stay out of it completely. So the more familiar you make this stuff, the more you say it to yourself and you write it, you go to take the test, and then you might see something on the test that doesn't look like something that you've done before. Take a few conscious breaths through your nose and tell yourself, I've done this before. I can do it again. This is no big deal. No one's going to die, right? Because as soon as you get that fear response from something looking unfamiliar, so how do we prepare? We make it familiar. There's an old saying in mathematics, right? We don't learn math. We just get used to it. This is trig sub type 2, because it's a sum, right? It's a sum of squares. Also, I have a coefficient in front of x squared. So this is the problem right here. This is the problem, except we're just going to have to switch some things up because we have bounds. But this one here, I've got a 4 attached to my x squared. That's weird. I've got a 3/2. That's weird. And I've got bounds. Okay. So this is the killer, right? So this is x is equal to a tangent theta. I'm breathing through my nose. I'm nice and calm. I might even make a note. I already know that 4x squared plus 9, this is pretty crazy. If this was to the 1/2, this would still equal, nope, let me write it like this first. Let me write x squared plus a squared to the 1/2 is going to equal a secant theta, right? I know that. We memorized that. That will always equal a secant theta. Penmanship's a little off today. If you have any trouble with that, say something. It's going to try to autocorrect me to come up with something goofy. A secant theta. So what I'm guessing is that this is going to give me 3 secant theta cubed. That makes sense, right? And if I get that, I'm going to throw a little party. Okay, so the first thing I'm going to do is go 2x is equal to 3 tangent theta. Because I no longer got x squared. I've got quantity 2x squared. Does that make sense? All right. You guys seem sad. You're not sad, are you? All right, good, good. Now, look, I don't have a dx on the inside, so you can do this. There's a few different ways, but remember, your primary mission right now is to make your substitution and then take the derivative. Make your substitution and then take the derivative. 3 over 2 tangent theta. Maybe I'll do that. You know, it doesn't really matter. I just want to make sure I've got this dx is equal to 3 over 2 secant squared theta d theta, right? So the derivative of tangent is secant squared. The derivative of secant is secant tangent, right? If I'm not familiar with that, every time I see it, I might want to repeat it to myself a little bit. The derivative of tangent is secant squared. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. All the cos are negative, right? I'm going to give you a little bit on that later on. Okay. So I got that. Now, what was my next step? My next step was to plug everything in. Substitute. I can't substitute if my bounds are wacky. So it looks like my dog is joining us. Okay. My bounds are a little wacky. So step 2, when you got bounds, you've got to change your bounds right away. When you've got bounds, you got to change your bounds. So what I'm going to do is say theta 1 is equal to 0. That's my bottom bound. Or I'm sorry, x1. X1. So my bounds up here are x values. Those are x values. They have to become theta values. They have to become theta values. Now you can call them theta 1 and theta 2 and take care of it later if you want to. But right now I want to say that 2 times 0 is equal to 3 times tangent theta 1. Well, the only way you're going to get 0 out of tangent is if theta 1 is equal to, it's sine over cosine. So that's 0. So theta 1 is 0. Okay. Then x2, the reason I got to do this is because I'm moving into theta now. I can't be in x anymore. I'm going to have d theta, not dx. So this is 3 square root of 3 over 2. So I'm going to plug that in. 2 times 3 square root of 3. And just know that this is magically going to work because that's the way it's rigged. All of these problems are rigged. Right? Because see, these are going to cancel. Those are going to cancel. And when does tangent, hopefully they don't hit you with this. I don't have this memorized. Square root of 3. That happens at pi over 3. So theta 2 is equal to pi over 3. So I've got my new bounds. I don't have to go back and write any triangles or back substitute. I'm pretty much home free at this point. Because step 3 is going to be now plug everything in. Okay, so I'm going to go from 0 to pi over 3. Okay. Now look, I've got to simplify this guy in the bottom. Maybe let's take care of that before we do anything else, because I don't want to carry all this baggage with me. Right? So I stop here and I say, all right, before I do any of that, I'm going to go 4x squared plus 9. You can put it to the 1/2 power if you want to, if that makes your life easier, right? Or you can just simply notice that, we'll do the same thing we did with the x squared plus 1. How about we just say here that this is going to be 9 tangent squared theta. That's what 4x squared is. Remember what your substitution is. Remember what your substitution is. Okay? Plus 9. Well, that's equal to 9 times 9 times tangent squared theta plus 1. And then sooner or later, you do this enough times, muscle memory triggers you, and you say this is 9 secant squared theta. So if that was inside a square root, it would be 3 secant theta, exactly what we thought it was going to be. See, if this was in a square root, we know it's going to be that. All right, so it's a little extra work in the beginning to memorize this kind of stuff, but I'm telling you, it pays off because after you do, 3 problems, 3 to 5 times each, right? You don't want to do a whole bunch of different problems. You want to take a few good problems and repeat the crap out of them. That's really what you want to do, right? So I have that. Now I need to figure out is what the square root cubed is going to be. So if I have 4, so what I'm looking at is I want 4x cubed or squared plus 9, 3 over 2. All right. This is going to be equal to 9 secant squared theta, 3 over 2. I could take that square root first. If I take the square root, which is the 1/2, that's going to be 3 secant theta to the 3. You see what I did there? I just evaluated the square root. I got rid of the 1/2, right? Because that's all the 1/2 power is a square root, right? How are we looking? Guys still with me?
Yeah.
Any questions so far? I'm going a little fast. Now, what you want to do when we're done is you want to go through this problem on your own several times. Because if you could do this problem, you can do any problem where you have bounds. You can do any problem where the coefficient is not in 1. And you can do any problem where your power is not 1/2. See? So there's no sense in doing a million different problems. Master this one first. Master this one first. Then move on to other problems. Then you're going to say, like, whoa, I can do this because I've got the framework for it down. See, when I do the same problem several times, my brain is going to start seeing past the numbers and it's going to start seeing the mechanics behind the problem. And that's what I want because that can transfer into a whole bunch of other problems. Okay, so that's going to be my denominator. So let's set this thing up now. We've got 0 to pi over 3. On the top, I've got x cubed. X cubed is going to be, let's just go like this. 3 over 2, tangent theta, cubed. That's x cubed. My dx is 3 over 2, secant squared theta, d theta. And then at the bottom, I've got 3 to the 3, secant to the 3, theta. Ain't that a mess? But I tell you what, it ain't that bad. Once I start simplifying here, you're going to see that's not that bad. Okay. So I'm going to go on to another page. Well, let's do this. How about I pull the 3 cubed, 2 cubed out? I'm breathing through my nose. I'm nice and calm, right? And then I've got 1 over 3 cubed, right? Integral 0 to pi over 3, right? 0 to pi over 3. So I pulled out all those constants. Tangent cubed theta, secant squared theta over. Notice I'm not doing a whole. I could cancel those secants if I wanted to, but I'm not focusing on that right now. I'm focusing on pulling out these constants because they're really annoying and they're going to simplify and life's going to be amazing, right? But right now they're just kind of bothering me. Okay. Any questions on what I just did there? Remember, it's all procedure. It's all procedure. Focus on the procedure. Okay, so I've got to, get rid of some annoying things here. I'm going to get rid of those, and so then I'll have what, 3 over 2 to the 4, which is 16. Okay, integral 0 to pi over 3. And I'm all cool. I'm breathing. I got tangent cubed theta over secant theta. See, if I start looking, if way back here, I'm looking at this and I'm going, oh shit, that's going to be so difficult. What am I going to do? Oh no, oh no. See, I'm getting a fear response right now. Oh no, don't worry about any of that stuff. Focus on one little thing at a time. You're chopping wood, right? I'm going to pull out this and this. That's all I'm going to worry about. So I do it. Okay, now I'm going to focus on, getting rid of these guys. Okay, I do that. Now I'm here and I don't know what to do. Right? But there's got to be something. Now, like I said before, before we had that cotangent squared thing, if we did 20 problems, that's going to come up. What I'm about to do right here, that would come up. So really, there's not a whole lot of things going on here because all these problems are cooked, you're going to get the same anomalies happening over and over, right? So I've designed these problems right here to spring those anomalies. So once you see this, don't say to yourself, I would never know to do that on my own. I would never see that. No, say to yourself, now I know what to do in this situation. In this situation right here, you know what to do is, I don't know, I'm stuck. I've got tangent cubed over secant. I don't know. The derivative of secant is secant tangent. That ain't sitting on top. U substitution ain't going to work, right? I can't divide it out. I don't know what to do. So I'm just going to put it back in its primitive form and see if that works. This is sine cubed theta over cosine theta cubed, right? Because that's, and then 1 over cosine theta. Whoops, nope, sorry. Secant is 1 over cosine. So there's your tangent cubed, and then you're going to have cosine theta d theta. All right, I'm still not out of the woods. I got 3 over 16, 0 to pi over 3, and hopefully on the test it won't be some puzzle that you've never seen before. Hopefully it'll be something that you've seen in your practice. But this is just one more feather to stick in your hat, right? I got one more thing I know I can do here, because there's a trick to this. There's always a trick. Now, I would never see this. Most people would never see what to do right here. But later on, if you see it on a test, you'll know what to do. Any ideas? Maybe I'll just play with it for a second and see if something pops up. If I didn't know what to do, that's what I would do. I would mess around with this a little bit. I would go, okay, wait a second. You've got sine squared theta over cosine squared theta. That's interesting. Sine theta d theta. Now, what did we learn from trig integration? From trig integration, if you have a single sine by itself, and I can write everything else at cosine. So this is what we're going to learn when we do trig integration, right? In trig integration, okay, what you want to do is you basically pull off a sine and make everything else cosine, because the derivative of cosine is sine. Or I can pull off a cosine and make everything else sine. Or I can pull off a secant tangent and make everything else secant. Or I can pull off secant squared and make everything else tangent. Right? That's the whole idea of trig integration, is you pull off a derivative of, let's say I pull off the derivative of cosine. The derivative of cosine is negative sine, right? I've got it right here. So that tells me, can I write this as cosine? Absolutely. So once you get one little thing like this, ask yourself, can I write everything else as that's antiderivative? If the answer is yes, you got yourself trig integration. So this is 3 over 16. So this is a beast of a problem. But if you write it enough times, I think I did this one in the videos in the classroom too, because it's that badass of a problem. See, I can write everything as cosine now. And the derivative of cosine is negative sine theta up to a constant. I got it sitting right there. Boom. Right? So what if I said, all right, let's go another layer deep on this substitution, step 1. So see, the derivative of the more complicated function, the derivative of the inside of the more complicated function is sitting on the outside. That's classic U substitution. So you say U is equal to cosine. So this problem isn't meant to freak you out. This is meant to give you as hard as it's going to be. And if you practice as hard as it's going to be, you're good for the easy stuff, right? So du is equal to negative sine theta d theta. Negative du is equal to sine theta d theta. Now, look, I can change my bounds if I want to, right? Because that's always step 2. When you have bounds, you have to change your bounds, and it's getting to be kind of ridiculous here, right? This will be 0. So that means u1 will be equal to cosine of 0, which is equal to 1, right? And then theta 2 will equal pi over 3. U2 will equal cosine of pi over 3. And cosine of pi over 3 is 1/2. Right? Okay, so now I'm ready. I'm ready to go. So I'm going to rewrite this whole thing now. I'm going to go negative 3 over 16. Don't forget about that 16. Don't forget the negative that's going to come out, right? So you're going to get 1 minus u squared over u squared du. Okay, so you can see this guy right here, that's where that negative comes from. See? Boom, boom. Okay, and then I've got my cosine squared, that's right here. So you just want to go back and make sure you got everything accounted for, and then you have your bounds, which is going from 1 to 1/2. Guess what? If I don't like that negative sign, I can go ahead and change my bounds because that makes more sense, doesn't it? And you're doing this on your own. You're going to get quicker and quicker at it. And you're going to get, the most important thing is you're going to get comfortable with it. Right? If you can get comfortable looking at this, that's when you got it, because really what's happening to your brain right now is fear. Your amygdala is firing. You're looking at this going, this looks crazy. I'm gonna fail this test. I'm gonna fail out of school. I'm never gonna get a job. Nobody's gonna love me. I'm gonna die alone. Right? You're going through this whole fear response. Right? Instead, you just breathe in smooth. I have seen worse. I've seen worse. This is as worse as it's gonna get. This is an absolute shit show. Look at this. Now look at this. You got 3 over 16. If you can do this one, you can do any of them, right? This is 1 over u squared minus 1. You see that? All I did was divide by that denominator. When you got a single denominator, divide by it. We're covering a lot of cool stuff right now. Whenever that happens, whenever you have an opportunity of a single denominator and a polynomial on top, divide. Divide. Right? And so let me rewrite this. I got to rewrite it in blue. That pink is really messing with my head right now. 1/2 to 1, u to the negative 2, minus 1 du. I can easily do this. And since I had bounds the entire time and I changed my bounds the entire time, as soon as I integrate this, I'm done. 3 over 16, negative u to the negative 1, minus u. And I'm going from 1/2 to 1. 3 over 16. Here's what I like to do. Negative blank to the negative 1 minus blank minus 3 over 16. I'm going to dummy proof this thing. Negative 1, if I don't run out of space here. Yeah, it's getting ridiculous. But I'm almost there. I mean, if they give you a problem like this on the exam, it would be half of the exam. That's how long this problem is. But if I can work through it calmly, I've got it. So look, you got your top here. I plug in my top, and then I plug in my bottom. Because at this point in the game, whenever this happens, when you get down to this point right here, you are exhausted. You're exhausted. Right? And I made a mistake somewhere. Top minus, no, I didn't. Okay, so this is going to be 3 over 16, negative 2, minus 3 over 16. That is negative 1/2 to the negative 1. Guess what? That's negative 2 minus 1/2. And you could simplify that, take care of that, right? But it was a lot. It was definitely a lot. There's a lot to this problem, but there's so much to learn from this problem. Right? And if you can do this one, you can do any setup, because you have, look at this. You've got the coefficient of x squared isn't 1. You've got 3/2 right here. You've got bounds, right? So remember, when you've got bounds, your step 2 means change your bounds. Then you go ahead and write your integral, because at the bottom, you'll just be able to plug these in and you won't have to back substitute. So when you're doing any kind of substitution, if you don't have bounds, you go step 1, declare your substitution. Step 2, plug it in. Solve. Step 3, back substitute. When you do have bounds, it's step 1, make your substitution. Step 2, change your bounds. Step 3, plug everything in and evaluate. That's how you substitute. All right. Any questions? So hopefully my hope is that you're not more intimidated when you leave here than when you came here. Right? But I'm telling you, you practice, rewrite this problem and then rewrite this problem. Then maybe do it again. And you get so used to it, facing this dragon right here. You go on to do a different problem and you're like, okay, what do I need to do? I need to figure out what type it is. Step 1, does it have bounds? Does it not have bounds, right? If it doesn't have bounds, step 1, 2, 3, boom. If it does have bounds, step 1, step 2, switch your bounds. Okay. And you practice. You say it out loud as you do it. Doing work inside your head doesn't do anything. I can have all the crazy thoughts in the world I want to have, but until I go out on the street corner and start yelling them, they're not going to make a difference. Right. And I can tell you what I was doing 5 minutes ago, but I cannot tell you what I was thinking 5 minutes ago. Your thoughts aren't real, right? Unless I think them a lot, then they might become real. Okay. What do you want to do? So we've done all that. We got trig integration and integration by parts. And so I'll tell you the videos I made for these in the school, right? If you go to the school here, where is it at? Oops. Go to the classroom, techniques of integration right there. You've got all your integration by parts, trigonometric substitution, trigonometric integration, partial fraction decomposition. So all of these videos are on here, right? But are there any
Do you
ones?
have any videos on hyperbolic functions?
No, that's very rare. That's definitely
Because
you
that's
see stuff like that in North Dakota.
Yeah, it's so random and it's basically the same thing as regular trig, except some of the rules are different, right?
Yep.
Yeah,
Pretty much.
I would
Okay.
look those up. So you're talking about the integral of hyperbolic functions?
Not the integral. I have, let me see, it's a section of my um I'll pull it up if give me 1 second. Let's see. It's just like computing stuff with them. I don't know, it's just a section of the I don't think it's for integrals, just let's see.
My advice for hyperbolics is know their definitions, right? Know their definitions, derivatives, and integrals. Because it's like e to the negative x, right? Plus e to the x over 2 is like hyperbolic sine or something like that. They're really
Yeah.
kind of off base.
Yeah. It's like Yeah, like evaluate the indefinite integral sine h2x dx. And it's just 1/2 cos h2x plus c. So, I mean, that's easy because that's normal, but except it's not negative.
Yeah. Yeah. So I would memorize the definitions of hyperbolic sine and hyperbolic cosine, and then I memorize the integrals. And what they'll probably do is, like give you like a U substitution type problem. That's what I would expect. If they're gonna do hyperbolic sine, hyperbolic cosine, they might throw an x on the outside. They might do something like this: x hyperbolic sine of x squared dx.
Oh, yeah, that's one of the problems I have. Yeah.
There you go, man. See, that's the thing is that it only takes a few years of doing this every semester, and you start to see the exact same problems over and over and over. And that's what I want you guys to remember too. There's a small basket of problems I'm going to choose from, right? And I need to hit the ones that are going to be representative of the most things in that basket. So if you've got this memorized, I mean, what is the integral of hyperbolic sine?
Uh, cos hx plus c.
Okay. Yeah, I see. I never work, and you're not supposed to use red because it triggers fear because it's color of blood. Isn't that weird? Supposed to use blue because it's calming because it's color of sky. It's real, man. That stuff's real. So look, so what I'm going to do is say u is equal to x squared. See, this is substitution. 2x dx, clear the constant. So every time you substitute, you're doing the exact same thing that we did for trig sub. Declare your substitution, take its derivative, right? Because see, I've got this now. This guy right here is right there. So all I got to do at this point, number 2, is go 1/2 integral du. Just put a big blank space in there, right? Because that just covered my x dx. And then what goes on the inside is sine hyperbolic of u, right? And I can integrate that. That's 1/2 cosine hyperbolic of u plus c. And then step 3 is back substitute. 1/2 cosine hyperbolic of u is x squared, plus c. So you see by the chain rule what happens here. When I take this derivative, that x squared comes out and gives me 2x. Boom. I end up with that. That's all u substitution is. It's backwards chain rule. Yep. Does that make sense? Let me check one thing here. Okay. So hyperbolics, I would memorize the integrals, and then I'd also memorize definition. Isn't like sinh, I think is what they call it, sine h. Isn't that like defined as like e to the x minus e to the negative x over 2 or something like that?
Yeah, e to the x minus e to the negative x over 2.
I guess that right? Oh my God.
Yeah.
Yeah. So like I would know those two just if they're gonna pull this kind of stuff.
Yeah, I don't know because it says the exam is on lessons 1 through 9, and so do the exams I found from past years. And this is one of the sections of that, but the past year exams don't have these at all. So I don't know
Yeah.
if he's just like, I have no idea.
Nobody's gonna really use that. I mean, they hyperbolics were used like when they're building telephone poles, but nobody's ever used them since. So I wouldn't worry about it too much. I would just know the definitions.
Okay.
Is that your dog? She's my dog.
Yeah, she likes to jump up on me. She's slow.
Yeah, he'll do that too, right in the middle of the session. Okay. Did you want to look at parts or trig integration or anything else? Parts is actually, I mean, that's going to be a big part of the exam, and it's super easy to do. Have either one of you guys looked at the videos on parts?
Yeah.
Yeah. So you can see from the videos, you got like type 1. That's every time you have a power times an exponent, a power times sine, or a power times cosine, you just do the table. And then anytime you have e to the x times sine of x, e to the x times cosine of x, you use a table over and down, straight across. Right. And then anytime you can do inverse trig functions or a power of x times ln. A power of x times ln is always going to be integration by parts type 3. And I saw one, I think it was on yours, Kayla, where it was like they had the integral of ln of x over x squared. And this is meant to fool you, right? Because if you have ln of x over x, that's u substitution, right? But if I look at it like this, a power of x, doesn't matter if it's positive or negative, this is parts type 3. In parts type 3, we use the table, but it's just basically regular old integration by parts without a table. Just that the reason we use a table is because if you have like x for type 1, if you have x cubed, you're gonna have to do that 3 times. And for type 2, you always have to do type 2 twice. So instead of doing it a whole bunch of different times, you just use a table. But for type 1, it's just one repetition. So you'll just do the table over and down, then straight across. Right? See, if I go plus minus right here, my U will always be equal to ln for type 3. And this guy will always be x to the negative 2. It'll always be the power. So I take the derivative and get 1 over x, or x to the negative 1. And then here I integrate it, so I get negative x to the negative 1, right? Okay. So what you do here is you go over and down, and then you go straight across. Because what that is that's u times v minus the integral of v to u. See, when I'm doing type 1 and I'm going over, down, over, down, over, down, that's evaluating this every time. That's what the table does, right? So if you have to do a lot of times, we have to do integration by parts multiple times, the table protects us from that. But when you're doing type 3, you're really just doing the table. See, my u times v is going to be negative. So this would be negative x to the negative 1 ln of x minus the integral. What's minus minus, right? Because you're going to have a negative inside. So that's plus. Let me write it as minus minus so you can refer to the table above it. Negative 1 over x to the negative 1 dx. See that? So when you do this, you've got, you can write this as x to the negative 1 or ln of x or whatever, right? But this will be plus integral x to the negative 2 dx. So you just integrate. So when I integrate that, I'm going to get negative x to negative 1 plus c. Right? Does that make sense? Now, there's a formula for this. If you have, what's great is that integration by parts, you always have a general formula. This will always end up being 1 over n plus 1, x to the n plus 1, ln of x, minus 1 over n plus 1, quantity squared. And in this case, it's just a 1. So n plus 1 is just negative 1. So when you square it, you just get that, right? X to the n plus 1 plus c. And you can see that that does match up perfectly. That's what it'll always end up being. So maybe I get that, and maybe I write it down, maybe I don't. But, if you're doing this and in the end, you're doing, let's just say it's x to the 3 ln of x. And in the end, you get 1 over 4 x to the 4 ln of x minus 1 over 4 quantity squared x to the 4. It's triggering that thing inside your brain that says this is familiar. So look, you don't have to memorize this at all. It's just maybe I make a little note of that every time I do integration by parts type 3 and I'm doing this and I'm not doing it on an exam. I write that down at the bottom and I see how it matches up. Because I can guarantee you, if you were doing x to the 3 ln of x dx, at the end, you will get 1 over 4 x to the 4 ln of x minus 1 over 4 quantity squared x to the 4 plus c. That's what you're always going to get. Right? So if I know the answer ahead of time, when I get it, or if it just looks familiar, hey, that looks familiar. I know it's something like that. And you feel good moving on to the next problem. See, when you get, you've had this experience on an exam before where you're taking the exam, everything's going great. Then you see something that doesn't look familiar and boom, all bets are off. Life's over, right? We're all going to die. Right? And that's that amygdala response in your brain. So you just want to be as calm and cool as possible. The best trick I ever learned it's almost like taking a beta blocker, right? Which just quiets that whole system down, is before your exam, you sit down, you find your territory, right? Breathe in and out through your nose. Mouth breathing triggers that sympathetic nervous response. You get out a piece of paper and a pencil, and neuroscientists taught me this. Get out a piece of paper and a pencil, and you just start writing down everything you're grateful for in your life, all the good stuff in your life. I got clean drinking water. I got a roof over my head. I got a car. Whatever you got, you do that for like 10 minutes, and that will shift you into the parasympathetic state, and you'll be nice and calm for your exam. Every time I do a public speaking engagement, I do that. And the times I forget, I get stage fright. The times I don't forget, everything runs smooth, right? Trust me on that. Yeah, everybody I know who does that before a test, who's tried that, says they have a different testing experience because you're not in that fear response, right? All right. So that's type 3. Okay. And you can do if you've got this ln of x over x dx, you can use u sub, or you can also use parts type 3. But I would just use u sub because the derivative of ln of x is 1 over x. It's sitting right there. If it's sitting right there, take it down. Right? Okay. Any other questions about parts? Because those videos are really good. I feel like those videos are good enough if you're understanding what they're saying. But there's always your trig. So once you get your trig integrals down, you start to see the pattern of what's happening. So if you have something like, well, first of all, let me just tell you, if you've got cosine squared or sine squared, you always have to write this as 1/2 the integral of 1 plus cosine 2x. This is the only way to do even powers of sine and cosine when they're by themselves. You have to use your half angle identity. That's just what you have to do. All right. But if you get, okay, let's say you have cosine cubed x sine squared x. When sine or cosine are together, you're looking for the odd power, right? When the power of cosine x is odd, that means you're going to take u and set it equal to sine x because your derivative du is going to be cosine of x. So these are always u substitution problems, and they're all cooked. I'm telling you, they're all cooked, right? You're not going to get anything too goofy for these. Because see, what I can do here is I can pull off, I can go cosine squared x, sine squared x, cosine x, dx. Okay. Now, I want to write everything as sine. Is there a way to write cosine squared as sine? Sure there is. 1 minus sine squared. So the more times I see this, the more times I see that cosine squared is 1 minus sine squared, the more comfortable I'm going to get with that idea, and it's just going to flow off the tip of my tongue. See, now I got everything I need. This is just 1 minus u squared du. There it is right there. So with cosine and sine, the power of cosine is odd, pull it off, set your u equal to sine. Power of cosine is odd, u is equal to sine. Power of cosine is odd, u is equal to sine. Power of cosine is odd, u is equal to sine. I said that for 15 seconds, maybe 10. You say it for 60 seconds and you kind of get a rhythm going, right? How'd you learn your ABCs? The rhythm of a song, right? You learned 26 characters before you even knew how to read at like the age of 6 because of a song. Right? So you say it enough times, your brain gets that rhythm going, right? So if I had sine to the 5, cosine to the 4, I do the exact same thing, except I set u equal to cosine because the power of sine is now odd. You see that? You're taking advantage of your trig derivatives. And just real quick, let me do a little side note, right? Trig derivatives. I know you guys probably know these, but they can't be anything that you think about. So you're going to write this table, right? If I have any trouble with these, I write this table and I start with cosine. I say all the cos are negative, sine goes with cosine. All the cos are negative, sine goes with cosine. Then I do sine. Sine goes with cosine. Derivative of sine is cosine. So that way, when I go to take the integral of sine, I write negative cosine instead of what everybody does when they take the integral of cosine, they write negative sine. That's not right. Right? And then sine over cosine is tangent. Sine over cosine is tangent. Tangent goes with secant. The derivative of tangent is secant squared. The derivative of tangent is secant squared. Now, what is 1 over cosine? 1 over cosine is secant. 1 over cosine is secant. 1 over cosine is secant. You see what I'm doing here? I'm just repeating this. And secant goes with tangent. The derivative of secant is secant tangent. The derivative of secant is secant tangent. Derivative of secant is secant tangent. All the cos are negative. 1 over sine is cosecant. See, I'm doing the one right next to it. 1 over sine is cosecant. 1 over sine is cosecant. 1 over sine is cosecant. All the cos are negative, and cosecant will always go with cotangent, just like the Pythagorean identities. They go together just like those Pythagorean identities. 1 over tangent is cotangent. All the cos are negative, and cotangent goes with cosecant. Negative cosecant squared. And then maybe just for shits and giggles, I write down sine squared x plus cosine squared x equals 1. Those go together. 1 plus tangent squared x. Those go together. Secant goes with tangent. Secant goes with tangent, right? And then I have cotangent squared. Cotangent goes with cosecant. So writing this table a few times is never a bad idea, right? Especially if I have to sit and think. If I've got to sit and think about anything, like as far as this stuff is concerned, it's just not gonna, you're gambling at that point, right? If it doesn't just come to you, right? So I do a problem like, so I say to myself, cosine odd, sine odd, secant even, tangent odd. Sine odd, cosine odd, secant even, tangent odd. And the thing with secant, that'll behave the same way as cosecant, except with all the negatives. Tangent will behave the same way as cotangent, except with all the negatives. But if I'm looking at secant even, tangent odd, say I have secant to the 4x, tangent squared x. What I'm looking for is the even power of secant. Secant x power even. So even powers of secant and cosecant, that trigger me. Odd powers of tangent, cotangent, sine, and cosine, that triggers me. To say that u will be equal to its partner. When the power of secant is even, u is equal to tangent. When the power of tangent is odd, u is equal to secant. When the power of sine is odd, u is equal to cosine. When the power of cosine is odd, u is equal to sine. You see it? Right? You just tell yourself this and tell yourself this. You tell yourself this tonight before you go to bed. And then you tell yourself tomorrow in the morning when you wake up, if this is the part that you're having difficulty making it stick, right? So this stuff is really hard to stick, right? Because it's not stuff that you're seeing in your daily life. You're only seeing it here, and this is very abstract, right? But if I say du is equal, or u is equal to tangent, du is equal to secant squared x, and look what I got right there. I've got that. See, I've got it. Secant. So this is why we say when the secant power is even, set it equal to tangent, because that derivative is going to give you that right there. So you just pull it off. Whoops, dx. And I want to write everything as tangent. If I want to write everything as tangent, I have to write that secant squared as tangent, and I can do that. Secant squared is 1 plus tangent squared, because I've said it to myself. I said it to myself. You can pace back and forth in your room and just say this stuff over and over to yourself. 1 plus tangent squared is secant squared. 1 plus tangent squared is secant squared. See it in your head. Write it on a big whiteboard. Take a whiteboard marker. Write it on the mirror in your bedroom. Whatever you got to do. If you're having trouble memorizing it, you just repeat it over and over. And you don't tell yourself things like, stories like, I'm never going to remember that. I'm never going to remember that. Because whatever story you tell yourself, you're going to believe. Trust me on that. Right? If I tell myself, I'm never going to remember this, you're going to believe it. Right? There you go, man. You're done. All you got to do is go, all right, this is the integral of u squared plus u to the 4 du. You'll start to see that all these look the same because you get these really weird powers. U to the 3 plus 1/5 u to the 5 plus c. That is equal to 1/3 blank cubed. See, I'm working on one thing at a time. I'm just going to put blank spaces in there. I'll worry about that stuff later. See, my u is equal to tangent. My u is equal to tangent. There's my u's right there. Tangent, tangent, tangent. And I'm money. I'm done with the problem. So I just have to repeat these things to myself. And if you watch these videos on school, I do that. I just repeat that same, you know, power of secant is even, u is equal to tangent. Power of secant is even, u is equal to tangent. Pull off the secant squared, pull off the derivative of tangent. Pull off the derivative of tangent, write secant squared in terms of tangent, because secant squared is 1 plus tangent squared. Right? You say that to yourself enough times, you're gonna begin to believe it. Right? Right on. How you guys feeling? It's been about an hour and 50 minutes. This is where we start to like, your brain starts to hurt a little bit. Yeah. Yeah. I'm going to try to do this more often, these group sessions like this. Over the summer, I've got a little extra time. And so be on the lookout. I'll try to post them ahead of time. But if I like have a cancellation in my schedule and if I can go live, if you want, I'll send there's only 4 people taking Calc 2 on school right now. So I can send you guys all a text and be like, hey, I'm going live in 10 minutes. If you can make it, cool. If not, I'll record the session. Right? Just like hopefully we're doing right now. Yeah, it's recording. And when you're doing cosecant, see, the reason I only do secant and tangent and sine and cosine is because that's what we tend to use. But if your teacher's an asshole and they want to do this, right? Cosecant and cotangent, they can throw those in there, but that's the same thing. It's cosecant power is even, cotangent power is odd. So the secant and the tangent will behave the same way as cosecant and cotangent will. So you don't really have to memorize that case. You just have to know what these derivatives are. Right. All right. Anything else? Any other things you want to talk about? Integration by parts, trig integration. I feel like we've got this down. All you got to really remember is that these guys right here, sometimes they throw them in, which I don't understand because it's just a formula. These are half angle formulas. That right there is cosine squared and sine squared is that. And that's the only way you can do even powers of sine and cosine when they're by themselves like that, unless you've got an odd power attached to it. Then you can run this trick. Yeah. But I've got more time if you guys have questions. Kayla, your test is on
It's tomorrow.
tomorrow.
Well, it's a self-paced course, but I'm taking it. I'm just choosing to take it tomorrow.
Okay. So
Yeah.
I'll work on your, you want to see solutions for those practice tests you sent me, right?
Yeah, that would be great if you have time. If not, no worries. I'm feeling pretty ready, so we'll see.
Okay. Yeah, I'll work on those. And then Caden, yours is until the 12th, right?
Mine's also self-paced, but that's the latest that I could take it.
Okay. I'll just take all those slides and try to organize them into like one test, and then I'll make solutions for that test. Yeah.
Thank you so much for doing this. This was really helpful.
Oh, good. That's the goal. Yeah.
I agree.
You agree? Okay. Like I don't want to waste people's time and stuff like that, so if this is helpful, that's really good feedback. Because I've only done a couple live sessions and only like I've done like 6 and only 2 of them somebody showed up and there's only one person for each one. And I don't know how helpful it was. This is good to have that feedback. Yeah. So you sure you got nothing else you want to talk about?
I'm good, unless Kayla has something.
Okay.
I think I'm good. I just have to make sure I have everything memorized. But in terms of actually solving the problems, I know the steps, so should be fine.
Good. That's the most important thing. And Caden, you have those with like Simpson's rule, those approximation integrals. Memorize Simpson's rule, the formula, and then memorize the trapezoidal rule. and the errors, the E sub t and the E sub s, memorize the formulas for those two. That's all it's about. And I'll write up solutions. I'll get started. I should have something for you by the end of tomorrow, Kayla. I'll get cracking on it as soon as we get off the phone here.
Thank you. No rush.
Okay, you're welcome. And if you guys need anything, remember, stay on that school site, stay connected on that school site. Send me text anytime you want, and I'll be texting you too to let you know about anything that might be upcoming or whatnot.
Perfect.
All right, good session.
Thank you.
you.
You're welcome. Bye.
Bye.